Think about the mechanics of playing a magnetic tape. A motor turns, gears lock, and a magnetic head reads a continuous physical signal. The hardware of a VCR was built for direct translation. You pushed a mechanical button, the internal spools moved, and the machine blindly pushed that analog feed out of the back port. It was a simple, dedicated pipeline. The tape held the complete uncompressed signal, and the cathode ray tube displayed exactly what it was fed. We still use the words play and stop, but the modern infrastructure of digital video shares zero DNA with those physical mechanisms. Because we drag and drop icons on our desktops, it is easy to assume an MP4 is just a digital VHS tape, a single solid object you hand over to a media player. But a digital video file isn't a continuous physical signal. It is a meticulously organized architectural package. Making it work requires a synchronized protocol of encoding, multiplexing, containerization, and decoding. If we want to understand why a stream buffers, stutters, or corrupts, we have to abandon the idea of simple video files and start mapping the digital delivery pipeline from the sensor to the screen. That pipeline begins the exact fraction of a second a camera sensor registers light. Early digital capture hardware took those photons and converted them into pure math. The baseline format for this raw digital capture is often YUV, a color space that separates the pure brightness of the image from its actual color data. But recording uncompressed YUV data creates an immediate bottleneck. We can see this by looking at a standard 422 sampling rate. This block details the math. A 422 video signal requires processing 4 samples of luminance for every 2 samples of color. When we multiply those samples by the standard base frequencies, we get a raw data burst rate of 27 megabytes every single second. Faster, more urgent tone. Over an hour, that single stream scales into massive server loads that a standard consumer network cannot reliably transport. Raw digital reality is simply too heavy to transmit. So the absolute first step in the pipeline must be an aggressive reduction of the data itself. This brings us to the first digital intervention layer, the codec. As this table shows, a codec is an algorithm, not a file format. It encodes heavy, raw data into a fraction of its original size. Codecs use either lossy compression, permanently discarding invisible data, or lossless compression for perfect reconstruction. They act as mathematical translators, taking an older, heavier standard like MPEG and compressing it into a highly optimized format like H.264. But solving the weight problem creates a timing problem. Video and audio are compressed by separate codecs at varying rates. Left alone, the audio track would rapidly drift out of sync with the picture. Shrinking the data is only useful if we can reconstruct it flawlessly. A lightweight video stream fails the moment it loses synchronization with its audio. We need a mechanism to lock these independent audio and video streams back onto the exact same timeline. That mechanism is the multiplexer, or muxer. It acts as the mixing agent, joining those distinct, separately encoded streams together into a single, cohesive track. Once that fragile synchronization is established, it needs to be protected for transport across a network. This is where we introduce the container. This column lists MP4, MKV, and AVI. These are not types of video. They are containers designed specifically to hold multiple multiplexed streams securely in place. You can think of an MP4 as a highly specialized zip archive. It provides a strict set of rules for how to store the streams inside, but it dictates absolutely nothing about what those streams actually are. An MP4 is just the shipping crate. It's a meticulously organized box holding a synchronized payload, prepped to be handed off to a delivery network. With our media packaged, we move from local storage into the actual transit ecosystem. Network playback relies on a strict client-server dialogue. One machine holds the data, and another sends a request to view it. This system map outlines a standard DLNA environment. The server, often a network-attached storage device, hosts the containerized files and waits for incoming connections. Those requests can originate from the edge devices on the right, like a smartphone or a smart TV. However, a mobile phone connected to a cellular network does not have the processing power or the bandwidth to parse a massive, unoptimized file. This creates a bottleneck. The server might be holding a dense, high bitrate 1080p master file, while the phone only has the bandwidth to receive a fraction of that data. To prevent the stream from failing entirely, the server employs a transcoder. The transcoder sits between the server and the client. It intercepts that 1920 by 1080 base file, actively scales it down to 640 by 480, and streams that lighter version out. Network delivery is never a passive transfer. It is a constant, active negotiation that dynamically alters the media structure to ensure it survives the journey. Once those data packets hit the end user's device, that entire architectural stack has to be instantaneously reverse engineered. The local media player interprets the rules of the container, and a demuxer actively tears the audio and video streams apart. Those separate streams are fed into local decoders, where algorithms expand the compressed packets back out into their original spatial coordinates. But we still face a final hardware hurdle. The monitor cannot interpret native YUV video data. The screen only understands precise red, green, and blue pixel values. As this diagram details, a system-level driver must intercept that YUV stream and execute a real-time color space conversion to RGB before passing it to the graphics card. Rendering a single frame to the screen requires one last microsecond of hardware translation, turning abstract digital math back into visible color. When we step back, we can see the complete anatomy of digital playback. Capture, compression, multiplexing, networking, and decoding all operate as a single, tightly coupled system. And driving this system are industry-standard tools like FFmpeg. Its primary job is simply to act as the core engine powering these endless high-speed conversions. A digital video does not exist as a static object. It is an active protocol of continuous translation, orchestrated millisecond by millisecond across a sprawling network of hardware.